Okay, we move on to the next topic, differentiation. Okay, and there are 3 prescribed chapters. Okay, let's start off with the basics. Okay, this is what you learn in matrix math, y equals mx plus c, so it is a linear line, and then the slope is equal to m, which is 2 in this case, and the slope is the same at all points along the line. But now we move on to a nonlinear function, this is an example, y equals x squared minus 4x plus 4. And then clearly the slope of this nonlinear function is not the same at different x values. So what we have to do graphically is to draw a tangent, and then at this tangent, then we would know, let's say for instance, you see this tangent is downward sloping, then we know, oh, at this x, this non-linear function has a negative slope. And then let's look at this horizontal line or the tangent, then it means at this x, then the slope is 0. We actually call it turning point or critical point. I will get back to this issue later. And then this is the last one. You see the tangent is upward sloping, meaning at this x value, this non-linear function is upward sloping. Okay, but we can sort it out mathematically by means of first order derivative. Okay, this is the mathematical explanation. Y as a function of x, and then the slope. There are 3 ways to express it mathematically, and this is called the first order derivative. So we have to differentiate this function y as a function of x once, and then to derive the first order derivative. And then we substitute the x value into the first order derivative equation, and then we will find out the slope. We call it instantaneous slope at this particular x value. And then there are certain rules, I think 8 rules in total. And then for all 8 rules, I provide examples actually on the slides and then the study guide as well. So this is the easiest rule, constant rule. It actually means there is no x at all in the function. This is a constant function, okay? Or graphically, it is a horizontal line. So if that happens, your first order derivative, which is the slope, is actually 0, as simple as that, okay? Next one, linear function. Okay, in case it is a linear function, y equals mx plus c, the first order derivative or the slope is simply your m. Then in other words, the slope of this actually linear function is equal to m at all x values. Okay, there are 2 examples here. This is the focus, power function rule. Now we really move on to nonlinear function, but we want to start with monomial, meaning there's only one term in the nonlinear function. So y is equal to k x to the power of n. And then the first order derivative is derived as you still have the k. Then you pull the exponent down, so k times n times x. Now the exponent value decreases by 1. It becomes n minus 1. So look at this example. The original function y equals 6x cubed. Then the first order derivative equation is 6 times. You pull the exponent down times 3 times x to the power of 3 minus 1. The exponent or the power decreases by 1. Then you derive your first order derivative equation 18x squared. Then you can substitute any x values you like to find out the slope of the nonlinear function at any x values you like. So for these 2 examples, you can see this nonlinear function is upward sloping when x equals 1 and x equals 2, but it is steeper when x equals to 2. Okay, happy with that? Then the sum rule, then we just move on to polynomial when there are 2 terms involved or more than 2 terms involved and there are addition signs involved, and then it is just the same old story. We simply apply the rules we learned earlier. So let's look at this one. The original function, y equals x squared plus 5x plus 6, and then the first order derivative is 2x. You know, you pull the exponent down and then the exponent value decreases by 1. This is how we get 2x plus 5. Okay, remember this constant falls away. Okay, so this is my first order derivative, and then we substitute any x value we like to find out the slope at that x value. And then similarly for the difference rule, once again polynomial, but there is a subtraction sign involved, then it is once again the same old story. So let me stop for 15 seconds for you to go through these 2 examples. Okay. And then we move on to the three more advanced rules. Okay, product rule. So this is the original function. Y is a function of s f x, which is the product of two, let's say, subfunctions, gx times hx. Then this is the first order derivative equation. It won't be given to you, so you need to remember that it is equal to gx times first order derivative of hx plus hx times first order derivative of gx. Okay, so this is an example. You clearly see the product of two like subfunctions. 4x to the power of 5, we can call it gx, and then 3x minus 2, we call it hx. Then this is the first order derivative of gx, 20 times x to the power of 4, and then first order derivative of hx is simply 3. And now we can find out the first order derivative of fx, which is gx times first order derivative of hx, which is 3 here, plus hx, 3x minus 2, times first order derivative of gx, which is, here, sorry, 20 times x to the power of 4. Then you do a bit of expansion, simplification, and then this is the answer, first order derivative. Okay, I can skip the next example. Quotient rule, this is the original function. Y is a function of y equals fx, it is equal to gx divided by hx. And then the first order derivative equation is, again, you need to remember that the denominator is easier, which is hx squared, then the numerator hx times first order derivative of gx minus gx times first order derivative of hx. So this is an example. You clearly see one term divided by another term. So this is my gx. Then I derive my first order derivative of gx. I think you can understand why you get 18x squared here. Then this denominator term is my hx. Then the first order derivative of hx. And now I make use of this equation to derive the first order derivative of fx, which is, let's start off with the denominator, hx squared. Do you see the square there? This is hx. Numerator, hx times first order derivative of gx minus gx times first order derivative of hx. Then finally, a bit of expansion, simplification, then this is the final answer. And then again, you can substitute any x values you like to find out the slope of fx at any x value. I can skip the next example, again, detailed explanation. Then I move on to the last rule, which is the chain rule. Okay. It happens when I have this type of function. Let's say y is a function of x, and then you see this term 4x cubed plus 7 bracket, but to the power of 5. You don't want to expand this 4x cubed plus 7 5 times. It will take ages to do the expansion. This is why we use the chain rule. Okay, dy over dx is equal to dy over du times du over dx. Then you are going to ask the question, where does this u come from? U is actually all the terms within the brackets. So in this question, u is equal to 4x cubed plus 7. So in other words, y is equal to u to the power of 5. Okay, then I can derive this first order derivative, dy over du, isn't it equal to 5u to the power of 4? Okay, and du over dx isn't it equal to 12x squared? And then the first order derivative of fx is dy over du, which is 4u to the power of 4, times du over dx, which is 12x squared. Then a bit of expansion, 5 times 12 gives you 60, isn't it? Okay, x squared is here, but for the final answer, we don't want to show u, you have to show the x only. Then I have to put this term back. U actually is 4x cubed plus 7, and then brackets to the power of 4. Okay. And then there's another example. You can go through that on your own. This slide is easy. Higher order derivatives, it means you keep on differentiating the function for the first time, second time, third time, fourth time, fifth time, until it is impossible to do so. But for this module, we would only focus on first order derivative, which gives you information about the slope of the function. And then second order derivative, which gives you information about the shape of the function. Is it concave or convex? Okay, so this is the next part. Okay, I think I have covered this slide. So I'm going to make use of this function, non-linear function. You see degree, which is the highest exponent, is 3. So expect this function to have 2 turning points. Remember, number of turning points is equal to degree minus 1. So this is my equation in connection with the slope. First order derivative, 3x squared minus 12x. Then I differentiate it one more time to derive my second order derivative, 6x minus 12. Okay. Second order derivative, I repeat, it gives us information about the shape of the function. And then you can substitute the x values you like, and in case your second order derivative answer is positive, then it means the shape is convex. Convex would mean a happy mouth, happy face actually. And then if your second order derivative is negative, then it means concave or the unhappy face. And then one extreme case is when the second order derivative answer is 0, then we call it inflection point, but this is not prescribed for this module. So let's look at different x's. This is the first one. Okay, again, you must keep these two equations in mind, first and second order derivative. When x is equal to minus 6, then I substitute x equals minus 6 into my first order derivative equation, 180 positive, then it means upward sloping. And when I substitute it into the second order derivative, remember 6x minus 12 negative, then it means concave, the unhappy face. So graphically, it looks as follows. Upward sloping, concave, the unhappy mouth, unhappy face. Okay. Second case, when the x equals to 0, then the slope is equal to 0. The first order derivative answer is 0. Then we actually call it critical point or turning point. But the point is it maximum or minimum turning point? This is why we need the answer on second order derivative. And then you substitute x equal to 0. You get a negative answer. Then it means it is concave, maximum turning point. So keep this in mind when it comes to a maximum turning point. First order derivative is 0. And second order derivative is negative, concave. Next one, when x equals to 1, then first order derivative is negative, so it means downward sloping. Second order derivative negative, so concave, the unhappy face. Next one, when x equals 3, first order derivative negative, downward sloping. And then second order derivative positive, then it means convex, the happy smile, okay? Second last one, when x equals to 4, then I substitute x equals to 4 into the first order derivative. 0, then it means it must be a turning point or critical point. Second order derivative, 12, positive, then it means convex, happy face. Okay, then it means minimum turning point. So I repeat, for a minimum turning point or minimum critical point, first order derivative is 0. Second order derivative, positive, which means convex, the happy smile. And this is the last one, x equals to 6, upward sloping, first order derivative positive, and then second order derivative positive, convex, upward sloping and convex. And then at the end, I make use of the information I derive from the 6 points to do my graphical sketch. So indeed, there are 2 turning points. Okay, this is a nice summary. Okay, another nice summary, this time involving the graphical sketch. Okay, and there are plenty of questions for you in the in-class exercise, on the PowerPoint slides. And then on the study guide, okay. Yeah, I also give you quite a number of questions to do and providing the memo. So if you really follow the explanation, even for some questions, I didn't really ask you to do graphical sketch, but I still include the graphical sketch. Then you know, oh, for this one, when x equals minus 1.5, minimum turning point, meaning first order derivative is 0, second order derivative is positive. Yeah, okay. And then similarly for this one, chapter 1, question 6, I also do the graphical sketch, this time maximum turning point when x equals to 7, meaning first order derivative is 0, second order derivative is negative. Okay, but remember we want to apply the mathematical skills or tools on real-life economic problems. So in the next video, we are going to apply differential calculus on 4 types of questions. Revenue, which must be about maximization. Production, maximization. Profit, maximization. And then the last one, cost, which rather involved minimization.